So let me start. Okay, first of all, thank you very much for giving me this opportunity. So I am Tetsuya Hashimoto from National Johnson University. So today I'm going to talk about the origin of first radio burst implied from the cosmic stellar mass density evolution. So my talk today is based on recent publication in monthly notice in collaboration with these people. So if you want to read my paper, so please access this QR code. Okay, so let me get started. So this is my outline of my talk today. So this is again, I put QR code here. So let me start with introduction, which includes two questions. So what is first radio burst? And also, how can we identify, how can we constrain the origin of ecologies? And also, I will explain the problem in previous words. And then I will present how can we overcome the previous problems using our new methods in my talk. And then later I will talk about my results, and then discussions and conclusions. Okay, so let's start. So what is first radio burst? First radio burst, FRB, is a mysterious radio signal which is coming from extra galaxies. So the duration of this pulse is very short, which is only milliseconds. However, they are very bright, which is comparable to the 1 Jansky level. So 1 Jansky level is very bright in radio astronomy. Currently, we know that there are at least two different types of FRBs. One is non-repeating FRB, and another is repeating FRBs. So if you detect only one time FRB from the same astrophysical source, which is non-repeating FRB. But if you detect multiple FRBs from the same FRB source, then it is repeating FRB, so it's very easy. So far, so more than 500 FRBs have been detected by using CHIME. CHIME is Canadian radio telescope, which can detect so many FRBs recently. However, problem is, so we don't know what they are. So this is a problem. So therefore, revealing the origin of first radio burst is getting more and more important in astronomy and astrophysics. So, how can we identify the origin of FRBs? So here I show the progenitor here. So progenitor means astrophysical source which is emitting the FRBs. How can we identify progenitor? In ideal case, so if you can measure the position of FRBs very accurately, so actually you can really constrain the position of FRB on sky. In this case, you see only one astrophysical source within the error circle, meaning that you can really directly identify the progenitor of this FRB. So this is an ideal situation. People say localization here. However, in reality, actually for most of cases, actually this error sample is too large than to directly identify the FRB progenitor. So this is the problem that we are facing now. So let me summarize this point. The origin of FRB is still unknown. The problem is, so previous research trying to localize FRB position in the sky accurately to directly identify the FRB origins. Okay, this is a most reliable way to identify the origin of FRBs. But I would say this didn't work very well because only one successful case we have for galactic repeating FRBs. But for other FRBs, more than 500 FRBs, we don't have any direct identification. So in order to overcome this problem, so we change our mind to focus on the history of the FRBs by using more than 10 times sample before. So what is this history of FRBs? So let me explain this in next slides. So here I select the possible candidates of FRB progenitors, which include white dwarfs, neutron star binary, old stellar mass black holes, magnetars, young pulsars, supermassive black holes, and supernova. So there are so many things here. And the problem is, we don't know which is the case. So we want to constrain. So let me propose in this one that actually we can divide these possible candidates into two different groups. One is old objects, which has very long lifetime, say giga-year timescale. The number density of long object should be proportional to the cosmic stellar mass density evolution, because you know the stellar mass in the universe is dominated by old objects. Another category is young objects. So they have mega-year timescale, which is much shorter than old objects, only mega-year. The number density of young objects in the universe should be proportional to the cosmic star formation rate density evolution, because more or less. So basically, these progenitors are remnant of star forming activity in the universe. Point here is that, so this cosmic stellar mass density evolutions and cosmic star formation rate density evolutions, both of them are actually already measured from galaxy observations. So here I show the number density evolution of young objects and old objects, shown by blue and yellow respectively. The point is, number density of young objects in the universe should increase towards higher redshift. In contrast, number density of old objects should decrease toward higher redshift. So these two trends is totally different. That means by measuring the number density evolution of first living births, actually we can strongly constrain their origin. So this is our idea. Let me show the one clear example in astronomy. So there's a very clear example. Or this is another astrophysical source, which is long gamma ray burst. So long gamma ray burst is already known that they are associated with star forming activity in the universe. So in this paper, they show the number density of long gamma ray burst as a function of redshift, which are shown by black cursor here. This is number density of long gamma ray burst. As you can see, number density of long gamma ray burst increased toward high redshift. And in this diagram, so cosmic star formation rate density evolution is also shown by red curve. So red curve also increased toward higher redshift. So therefore, this cosmic star formation rate density and the number density of long gamma ray burst, they are kind of synchronized as a function of redshift. So this is one of the strongest evidence that long gamma ray bursts are really associated with star forming activity in the universe. So as you may know, it is already known that the progenitor of long gamma ray burst is explosion of the massive star. Okay, explosion of massive star, they are obviously related to star formation. So this is a very good example. So we really want to have FRB version of this diagram in this work. Okay. Then fortunately, as I mentioned, game changer has arrived last year. This CHIME, this is a Canadian radio telescope, is keep detecting so many FRBs, which is 10 times more than before. So why not use? So let's use this sample to calculate the number density history for FRBs. And here I again emphasize that our idea. If FRB originates from young object, young progenitors, number density of FRBs should increase toward a higher redshift. In contrast, if FRB originates from old objects, the number density of FRBs should decrease toward a higher redshift. So this is the point. So in the next slide, so I will show you our results. So guess what? So here I show our results. I show the number density of non-repeating FRBs from CHIME FRBs as a function of redshift, which are shown by red stars here. As you can see, the number density of FRBs decrease toward higher redshift. This decreasing trend is consistent with this decreasing trend of cosmic stellar mass density evolution. And also, this decreasing trend is obviously not consistent with cosmic star formation rate density evolution. So our result indicates that non-repeating FRBs likely originate from old objects, old progenitors. And then finally, let me compare our result with previous works. So, actually there are several similar papers which try to investigate number density evolution of FRBs. So here I try to select important factors in this kind of analysis because we want to investigate number density evolution as a function of redshift. So therefore, in principle, we don't want to assume any functional shape of redshift evolution part. So in this sense, we have advantage because we use the so-called Bmax method. I didn't tell you details, but we use a Bmax method which will allow us to directly measure the number density of FRBs as a function of redshift, as it is. So there is no assumption here. So we have advantage here. But for other papers, actually they have a model approach. They need to construct FRB population model. They need to assume certain shape of redshift evolution. Even though we want to measure the redshift evolution, from beginning they have kind of assumption. So that is not very good. So, and of course, this Bmax method allows us to measure any functional evolution type shape. Therefore, of course, we include testing the order population scenario in our study. Also, we use China sample, which is the current best effort, and the China sample is very homogeneous, it's very good to conclude the order population for FRB. Recently, there's another paper, Zhang and Zhang, 2022. They also use the China sample. They still use a model approach. They need to assume functional shape of redshift evolution part. But point is, they also get a similar result. They also indicate the older population will be the significant population, supporting our result. Okay, let me conclude. We used 10 times more samples than before, and then we found that non-repeating FRBs are likely originated from old objects, which may include white dwarfs, neutron star binary, and old Stellar-mass black holes. And then finally, let me advertise. Actually, in this ASRC, actually there are 4 other FRB talks. Therefore, if please also check their presentations. Okay, I stop here. Thank you very much.
So we take a question. Anyone? Yes.
So, thanks for your presentation. And I have a simple question about the introduction of FRB. So you mentioned that there are 2 kinds of FRB. One is non-repeating and another is repeating. So the problem of the localized of FRB is not precisely, right? So how do we know the repeating FRB is from the same sources because the localized the measurement of the position is still have large uncertainty.
That's a very good question. Thank you very much. So actually, for FRB has a very unique observable, so which is a so-called dispersion measure. So dispersion measure is, say, simply speaking, so time lag between different frequencies of FRB. And this time lag happens because the speed of light radio emission changes when it goes through the plasma. So therefore, we can measure dispersion measure. And then this dispersion measure is indicator of how much amount of plasma you have between FRB and the observer. Okay. And then if this number is really almost the same for repeating FRB, and then also within this large uncertainty or position error, they overlap, and then if they show the same dispersion measure number, that means they are more likely along the same line of sight because they are showing the same amount of plasma. So that usually when people identify repeating FRBs, they cross match positional sky position and also dispersion measure. So.
Nice talk. Yeah. So how reliable is the redshift determination of FRBs? Please comment on that.
Oh, thank you very much. I always get this question. very roughly speaking, it's 10 to 20% error. And then just for backup, actually for some FRB sample, actually there's a spec Z. So spec Z is the answer, true answer. And then using my method to calculate redshift for each FRB, which is shown in y-axis, and then as a function spec Z, then error bar is typically disordered, this kind of things. And then basically within error, spec Z and our redshift are consistent very much. And then for this analysis, actually we don't really need very accurate redshift measurement because we really want to know if it's decreasing or increasing. And then this is a typical size of the redshift error. And then in order to see that this trend, actually we don't, this size of error, redshift error, is small enough to differentiate between increasing trend, decreasing trend. Thank you very much.
Any other question? No? Yes.
Thank you for the nice talk. And I have two simple questions. As you say, the long downward burst is a good example for this feature. Are there any other example as good as the long downward burst? And yes. And the other question is, how about the repeater result? Do you have any answers for the repeater result?
Okay, thank you very much. As far as I know, supernova, there are so many observations in supernova. And as far as I remember, supernova also showed an increasing trend. But depending on type of supernova, some people say there's a delay from the cosmic storm mentioned density. But anyway, I think supernova is also another good example. And then, but supernova case actually the spectroscopic redshift is necessary, therefore that's the difficult part. But anyway, I think supernova is okay. And then for repeating melodies, that's also thank you very much, very good question. Actually, unfortunately, the number of samples for non-repeating melodies is still very small. I mean, number of repeating Hashimoto sources are very small. And then I actually tried to do this in this part. But actually, the number is too small to construct energy function and then correctly, it's very difficult to correctly estimate the number density because of the lack of the sample. So in future, yes, we have to do that. Thank you very much.
Yeah, we will stop here and then we'll go on to the next talk. Thank you for speaking.
Thank you very much.
So next